Single replacement reactions have a general form as shown here. A plus Bx goes to, say, Ax plus B. A is an element which is more active than B, and that is, it prefers to be connected to X more so than B prefers to be hooked up with X. So this generates an entire combination of reactions. For example, if we have zinc metal in the place along with copper, say copper sulfate, we just mentioned it a minute ago, in aqueous solution, this ion is replaced by a zinc ion. So this will go over and hook up into this salt and make copper go to a basic standard state. Go to a zinc sulfate, see where the ion replaces, and then that's aqueous plus copper solid in basic standard state at the end of the reaction. So there is a list of metals that says the order of replacement exists, and you'll find that in the handout I gave you. I think about the second page or so. Yeah, it is this list right here. If you have that handout, if you don't, I'll try to zoom in and show you how it works, and you can look on with a neighbor or something. But and this is kind of like top down. The more active elements are at the top of this chart, and the less active are below. And what that means in these reactions is that something at the top will replace something below it. That's the long and the short. That's the short version, and it works every time. Lithium will replace any metal below it. Potassium will replace any metal below it, but not lithium, because lithium's more active in the reactive process than is the potassium. And so you can go down, aluminum will replace all of the magnesium, zinc, and so forth, but not anything above it. So with this table, you don't have to memorize this table. Don't relax. With this table, you can predict the outcome of a single replacement reaction. So on the list, you'll find zinc will be above the copper in the activity series. Let me see if I can find that. Here's the zinc. And with copper, here's copper down here. So when you look at this, I'll try to put it right here. Zinc being above the copper, zinc will replace the copper, and copper will go to a basic standard state in the reaction, single replacement reaction, as shown in this example right here. So that's the long and the short of it. Now, that's one aspect of this reaction. Now, it is also an oxidation reduction reaction. So single replacement reactions, as well as the decomposition, composition type reactions, are oxidation reduction reactions. So we want to review that. So as you look at this, this is 0, and this is a -2, -2, and this is a 0. That's a +2 and +2. Now remember how to determine oxidation states of substances in your process. If I have aluminum as a solid reacting with tin, SnCl2, for example, aqueous, you have to apply the oxidation numbers to this, okay? In doing so, how do you determine what the oxidation states of the elements are in the, say, tin? Well, group 7 with chloride is always a fixed charge -1. So that you come in with a -1, and that gives you a net -2, and then your deductive reasoning tells you that should be a +2. So when you come over here and make the products of this, you want to hook up aluminum and chloride. However, the subscripts on here will not be what the subscripts are here. Just because this is a 2 doesn't mean it's going on the reactant side doesn't mean it's going to be a 2 on the product side. The subscripts depend on these oxidation states. So as it goes over, this becomes will substitute. Well, aluminum's a fixed charge element. This is a -1, and that is always a +3, like that. And so that would become a subscript 3 aqueous, and then the 10 would come out as a reduced form. So when you look at these, aluminum goes to aluminum +3, 0 to +3, and 10 goes from +2 to 0. So what's happening in here? 0 to +3 is lost 3 electrons, and +2 to 0 is gaining 2 electrons. So you need to be aware of that to apply the ideas that we've already talked about in oxidation reduction. So to balance the charge, I need a 3 here and 2 here, so I would come in here with the 2 aluminums, each losing 3 electrons, leaving me with 2 aluminums over here. And then I have 3 10 ions, 10-2 ions, each of those 3 gaining 2 electrons. And on this side, I would have to have also 3 over here, so you get this mass balance. Well, you don't have any oxygens or hydrogens in here, so it looks to me like everything, 2 to 3 is 6, 2 to 3 is 6, so everything's balanced. The sulfate in the examples and the chlorides in these examples are known as spectator ions. I may have mentioned that in the past. They do not react. Are not reactive in process. So if you have this page, it's the next page after the activity series. In this first one, it has a calcium replacing magnesium. Will that happen? Well, yeah, if magnesium is above the calcium on the activity series. So you go to the activity series and compare the position of the calcium and magnesium. So we find calcium here, and since magnesium is below it, calcium will replace the magnesium. It's just that straightforward. But you will also have to deal with, of course, writing the products over here. So when magnesium comes out and is replaced by calcium, the calcium, they're showing it as an ion here, but it will go in as an ion over on the product side also. Typically you will see these listed as, wait a minute, that's not an ion. No, that is basic standard state. I thought it was a plus. Anyway, it goes to calcium ion along with chloride ions, which are spectators, and the magnesium goes to basic standard state. So give a try to these and make sure you're comfortable with the replacement reaction, single replacement. Down here, you go through the reaction and predict the oxidation half reaction, reduction half reaction, and I suggest trying to identify the substance as an oxidizing or reducing agent. Of course, if it's an oxidation process, the substance is a reducing agent. And if the process is oxidation, then oxidation is a reducing agent and reduction is an oxidizing agent. So this entire sheet just orients you with the oxidation reduction as well as the activity series. And so please go through that. I think you'll be very straightforward in how these types of reactions work. Well, that leaves us with, and I meant the metathesis reaction.